Alright, let me ask you a question. Imagine you have an array of 1 million numbers. Someone asks, what is the sum from index 50,000 to 750,000? You could loop through and add them up. That takes O of n time. Fine for one query. But what if they ask 1,000 times, 1,000,000 times, and between queries they change some values? That is where segment tree becomes your best friend. By the end of this lecture, you will understand how it works and how to implement it yourself. What is a segment tree? A segment tree is a binary tree designed for two things: answering range queries and supporting updates, both in O of log n time. With a naive approach, query takes O of n, you scan every element. Update takes O of 1, just change one value. With segment tree, query takes O of log n, update takes O of log n. When you have millions of queries, this difference is massive. Key characteristics: binary tree structure. Each node represents a range of the array. Leaf nodes are individual array elements. Internal nodes store aggregate values like sum, min, or max. Space complexity is O of n. We allocate 4 times n to be safe. Structure example. Let us take array 1, 3, 5, 7, 9, 11 with indices 0 through 5. The root node stores sum of entire array, which is 36, covering range 0 to 5. Its left child covers 0 to 2 with sum 9. Its right child covers 3 to 5 with sum 27. We keep splitting until we reach individual elements. Those become leaves. Every node answers a question. What is the sum for my range? We store this tree in an array. Node at index I has left child at 2 times I and right child at 2 times I plus 1. Building the tree. Building uses divide and conquer recursively. Here's the algorithm. If start equals end, we are at a leaf. Store the array value and return. Otherwise, calculate mid as start plus n divided by 2. Recursively build left child for range start to mid. Recursively build right child for range mid plus 1 to end. After both return, set current node to sum of its two children. Time complexity is O of n because we visit each element once. This tree has log n levels. Total work is O of log n time. Range query. This is where the magic happens. Say we want the sum from index 1 to 4. At each node, we check 3 cases. Case 1 is no overlap. Node range is completely outside query range. Return 0. Case 2 is total overlap. Node range is completely inside query range. Return the node value directly. Case 3 is partial overlap. Recurse into both children and add results. For our example, we find nodes covering ranges 1, 2, and 3, 4 have total overlap. We return their values. 8 plus 16 equals 24. Why O of log n? At each level, we visit at most 4 nodes. The tree has log n levels. Total work is O of log n time. We don't scan all elements. We combine pre-computed answers. Point update. To change value at index 2 from 5 to 10, start at the root, determine which child contains index 2, go that direction. Keep going until we reach the leaf for index 2. Update the leaf value to 10. As recursion returns, we calculate each parent as sum of its children. Only nodes on the path from root to leaf are affected. That's log n nodes, so O of log n time. Code overview. 3 main functions. Build, recursive, if leaf, store array value, otherwise build children, then merge. Query, if no overlap, return 0. If total overlap, return node value. If partial, recurse both sides and add. Update, find path to leaf, update it, recalculate ancestors on the way back. Key indexing, left child at 2 times I, right child at 2 times I plus 1. beyond sum. Segment trees work for any associative operation. For minimum, merge using min. Identity is infinity. For maximum, merge using max. Identity is negative infinity. For GCD, merge using GCD function. Same structure, just change the merge operation. Complexity summary. Build O of n time O of n space. Query O of log n time. Update O of log n time. Compare to alternatives. Plain array is O of n query, O of 1 update. Prefix sums is O of 1 query, O of n update. Segment tree is best when you need both fast queries and fast updates. Applications. Where do we use this? Database range queries, game leaderboards with frequent score updates, stock price analysis over date ranges, competitive programming, very common topic. Conclusion. Use segment tree when you need range queries like sum, min, or max. Elements update frequently. Both operations need to be fast. My advice is practice building and querying. Use visualizers. Implement it yourself. The best way to understand segment tree is to see it work and build it with your own hands.